So, good day to everyone. Today is a nice evening to take some details about the transformers. So, as you probably know, the transformer is a fully static device. It means that it has no any moving parts. It's fully solid. It doesn't rotate, doesn't move, doesn't shake, and so on. So this device is required to change the voltage and to change the current, but it is not able to change the frequency. So it's always operate at the desired rated frequency, say 50 Hz or 400 Hz in aviation. You have to also know that transformer is not able to operate on DC power. So, the transformer can be three-phase, like this, or it can be single-phase. For example, I have to, now I have focus, For example, this small guy is a single-phase transformer. The single-phase transformers can be of three types. The first of them is a core type, like the core goes outside of the transformer and the windings are here. The second one is a shell type, when windings are inside, like in a shell, and the shell is made of the magnetic conductor. And the third type is toroidal. So, transformer consists of at least two windings. These are called primary and secondary, as well as it consists of magnetic conductor. And the magnetic conductor, this is the core of a transformer. The core is made of ferromagnetic material of iron, and to prove this I have this magnet, so I can attach this magnet, and as you can see it is held onto these pieces. So these pieces are made of steel, made of iron. So these are magnetic conductors of a transformers. The question is, why do we have to use iron instead of aluminum? Because iron has much more greater weight compared to aluminum. The answer is that only iron is ferrous material, so it is a really good magnetic conductor. In order to prove this, I will take this piece of iron, and here is the much more powerful magnet. So it attaches here. So, in order to prove that this piece of metal, this piece of iron is a really good magnetic conductor, I will attach it to the magnet. And then I will put this piece of metal inside in the washers. And as you can see, it is able to catch all these washers. So it means that magnetic flux strength lines go through this piece of metal and are able to be shortened on the tip of this iron. However, if I will take this piece of non-ferrous material, it doesn't hold here, So I will hold it tightly, and if I will put it in the washers, then the washers attach to the magnet, but they doesn't attach to this piece of non-ferrous material. So this is the key moment. Why do we are not able to use aluminum as a magnetic conductor? The second question is, why do we made a magnetic conductor of the separate plates? These plates are laminated core plates, and these are required these are required to reduce eddy current losses. So look, here is the pieces of the cores. Yeah, these are laminated core plates. This is for the shell type transformer. Yeah, and this is for the core type transformer, and this is for the toroidal. In the shell type transformer, windings are wounded on the center of the magnetic conductor, whereas remaining parts are required to make possible to short the magnetic flux trans lines. In the toroidal transformer, the windings are wounded like these around the core, in a similar way here. Yeah. And in a shell type, windings are wounded. I have no focus. Yeah. Windings are wounded like this. So, as was mentioned before, these plates are required to reduce eddy current losses, or so-called vortex currents. As you can see, electrical machines are also made of such plates. So the idea is to increase resistance between these plates, and when the resistance will be high, then currents will be low. In this case, vortex currents will not be able to circulate inside in the magnetic core and increase its heat. In order to demonstrate it, I will try to use this multimeter in order to measure resistance. Yeah. So if I take these two contacts together, then I get almost zero resistance. Now I will put one wire about the plate, yeah, and another wire outside of the plate. Now this doesn't want to stay here, but okay. So, or even like this. Yeah. If I measure the resistance, I can see that resistance is not zero. Yeah, it fluctuates, but it's much more than 1 ohm. Yeah. This is due to the fact that these plates are covered with oxide layer. So this increased resistance doesn't allow to build up vortex currents called eddy currents, and therefore the magnetic conductor will not heat. So okay, so now let's take some details of the principle of operation of a transformer. So here we have this small test bench, yeah, and here is the transformer. This transformer has primary winding, which is wound like this, secondary winding, which is wound like this. Both windings are wound onto the same core. This core is made of laminated core plates. Actually, this transformer has been created for the students, and therefore it is very robust. Yeah, and its robustness is proof that it's very old and still it is live. It doesn't dead. So this transformer got power through these wires, and this power is supplied by this variable voltage power source. Also, we are able to measure consumed power, real power, active, primary current, which flows through the primary winding, primary voltage, or voltage which is applied to the primary winding, On the schematic we can see variable voltage supply, this one, followed by wattmeter, power meter, which measures only active or real power in watts, this one, followed by ampere meter, this one, and also the voltmeter, which is attached here and which measures the voltage which is applied to the primary winding of a transformer. The secondary winding of a transformer is connected to the voltmeter. So secondary winding wires goes here, 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 and here is the voltmeter, as well as through the ampere meter. It can be connected to the load, which is not connected yet. So now we are able to check how does transformer operate at no load. From theory we know that transformer is able to convert voltage. How this voltage is converted is determined by the turn ratio, such a coefficient, turn ratio. So turn ratio is determined by the number of windings in the secondary winding divided by number of windings in the primary winding. Or, which is fully similar, EMF, electromotive force in the secondary winding divided by the EMF in the primary winding. So, how many EMF we have here? We don't know. How many windings, turns we have here? Again, we don't know. So this becomes a problem. So let's check the turn ratio experimentally. To do this, we will operate our transformer at no load. It means that load is disconnected. So I will apply some voltage to a transformer. At first I will enable power, and now I will apply the voltage to a transformer. So full range of our voltmeter is 150 volts. So I will apply, let's say, 100 volts. Here is it, So we have 100 volts, okay. As you can see, we also got some current which flows through the primary winding. It's quite small, 1 ampere scale, it's quite small, but it is here. The secondary current is equal to 0 because load is disconnected. And the secondary voltage also is rising up. So let's note these values. Primary voltage is 100 volts. Secondary voltage is 53. Also, we consume some power. The range is 300, so this is the 10 watts. Okay, now let's increase the voltage up to 150. So primary voltage is rising up 150. The secondary voltage has been increased to 80. The input power has been increased to 21 watts. Finally, let's go to the rated voltage. The rated voltage is 230 volts, so I have to switch the range to 300, so now the full scale range is 300. So 230 volts. The secondary voltage increases too. The secondary voltage now is approximately 108. The primary current also is rising up, but the consumed power is still very small, is approximately 26 watts. So, where is the joke? At first, we do not have any connected load, so we do not have any consumed current, so 0 times voltage give us 0, so we consume nothing. However, transformer consumes some power. It means that it consumes, but it produces nothing. Where is the joke? It's not a joke. Actually, these are losses. This is the eddy current loss, and these losses are cause increase in the temperature of the core. So it slightly increase its temperature. So these 26 watts are used to increase temperature of the core, and these are simply lost. So now let's calculate number of turn rate. So to do this, I will divide secondary voltage by the primary voltage. So 53 divided by 100, this is 0.53. 80 divided by 150 is equal to 0.53. And 109 divided by 230 give us 109 divided by 230 give us 0.48. 48, yeah. So as you can see, the turn ratio does not depend on how many volts we apply, how high voltage is, until we are within rated voltage or below it. So the turn ratio can be approximately calculated by means of voltage ratio, whereas the secondary voltage is divided by the primary voltage. So this is the real thing which can be done, yeah, in real environment. One more question. Here we have 0.45 amperes. So 0.45 amperes times 210 volts give us approximately 100. 100 of what? These are not watts. These are volt amperes. However, watts, real or active power, is negligibly small. It means that the majority of power, which was calculated here, this is the imaginary power, yeah? Imaginary or reactive. It means that the majority of this current is the magnetizing current. It doesn't provide any work. It is required to create magnetic field in the transformer. So okay, now I will put the voltage onto 230 volts. Okay, so now we are operating at no load. So load current, which is secondary current, is equal to 0. Applied voltage is 230 volts. Primary current is 0.6 amperes. And consumed power is 16 value, so it is 32 watts. Secondary voltage is near to 120, so I can say say this is the 119. Secondary power can be calculated by multiplying voltage by current, so we got 0. Now let's enable load. Here we have a lot of loads, but I will use this rheostat. This rheostat is a real load, so I can consider that cosine phi or power factor is equal to 1, so current times voltage is equal to active or real power. So let's enable it. So we got some current, and the current is 0.56. I have to check that we still have 230 volts, okay? So 230 volts, and the load current is 0.56, and secondary voltage now starts to drop. So the secondary voltage now is only 117 volts. Since we start to consume some power, we multiply current by the voltage, we got some power, then primary current increases too, and we got 0.73. And also we start to consume more from the power supply line, so we got 55 times 2, 110 watts, and by multiplicating 117 by 0.56, we got power of the output 66 watts. Power, in watts. Okay, now let's increase the load. So my ampere meter is approaching its limits, so I have to switch range to 5 amperes, and I will go to, say, 3 amperes. Similar problems are here, so I have to switch also this range. Okay, let's say 3 amperes, So I have to check that we still have 230 volts, it's not, so I have to slightly compensate. Okay, so I adjust the input voltage to get exactly 230 volts, and power meter also should get different scale. So now our wattage is times 4, so we got near to 440. Primary current is, so the full scale divided by 5, and remove 1 0. So this is the divide by 2, sorry, this is the 2 amperes. Voltage is 230, and the secondary voltage now is only 108 volts. Secondary current is 3 amperes, and secondary power can be calculated voltage times current. We got 330 watts. So what we got from here? At first, if we increase load, then output voltage starts to drop. This is caused by the internal resistance of both primary and secondary windings. So secondary If we increase load current, then also primary current, which consumes power from the wall socket here, this current also increases. Fully logical. We got less power on the output compared to the power on the input. From these two powers, we can calculate efficiency of our transformer. For example, at this point, this efficiency is 75%. Now I have to multiply it by 100%. Okay, what about turn ratio? Look, if you will use voltages as it was here, you will got wrong results, because 119 divided by 230 is not the same like 108 divided by 230. So this method is not applicable. So you have to remember that this one can be used only if your transformer is operating at no load. Yeah, so load must be disconnected if you would like to calculate your number of turn ratio. Also, we can calculate turn ratio by means of currents, but in this case you have to divide primary current by the secondary current. So these two are reversed, yeah, swapped. So again, primary by secondary. Primary by 0 give us infinitely high value. So we can't do this. Primary by secondary, here we can calculate, yeah. So primary is 0.73 divided by 0.66. We got 1.3, which is not true because the actual value is shown here. So let's divide these two currents. 2 by 3. It will give us 0.66, much more closer to our exact value. So we have to continue to increase load current. We have to get these values which has been not measured because my rheostat hits too much. Yeah. So this approach can be used only at the rated load. Rated, also sometimes called nominal. So you have two possibilities how to measure turn ratio: by means of currents at the rated load or by means of voltages at no load. So thank you, and I hope that you will pass your exams. So it becomes hot, yeah. So bye bye.